A Carnegie Institution for Science audio press release for September 25, 2014. Smallest possible diamonds form ultra-thin nanothread. A team including Carnegie's Malcolm Guthrie and George Cody has, for the first time, discovered how to produce ultra-thin diamond nanothreads. They promise extraordinary properties including strength and stiffness greater than that of today's strongest nanotubes and polymer fibers. Such exceedingly strong, stiff, and light materials have an array of potential applications, everything from more fuel-efficient vehicles or even the science fictional-sounding proposal for a space elevator. Their work is published in the journal Nature Materials. The team was led by John Batting, a chemistry professor at Penn State University, and his student Thomas Fitzgibbons. They used a specialized large-volume, high-pressure device to compress benzene up to 200,000 atmospheres. At these enormous pressures, benzene spontaneously polymerizes into long, thin strands of carbon atoms arranged just like the fundamental unit of diamond structure, hexagonal rings of carbon atoms bonded together, but in chains rather than the full three-dimensional diamond lattice. Batting explains that because this thread is diamond at heart, the researchers expect that it will prove to be extraordinarily stiff, extraordinarily strong, and extraordinarily useful. The long polymer threads made up of chains of carbon atoms bonded to each other, all threads being less than a nanometer in diameter. But also, from a fundamental science point of view, the discovery is intriguing because the threads that were formed have a structure that's never been seen before. The molecule they compressed is benzene, a flat ring-shaped molecule containing 6 carbon atoms bonded to each other and to 6 hydrogen atoms. After compression at high pressure, the resulting diamond-cored nanothreads are surrounded by a halo of hydrogen atoms. During the compression process, the normally flat benzene molecules stack together in a dense crystalline arrangement. As the researchers slowly release the pressure, the benzene molecules unexpectedly react with each other, forming new carbon-carbon bonds with a carbon configuration of diamond extending out as a long, thin nanothread. The team's discovery comes after nearly a century of failed attempts by other labs to compress separate carbon-containing molecules, such as liquid benzene, into an ordered diamond-like nanomaterial. Guthrie says that the researchers used the large high-pressure Paris-Edinburgh device at Oak Ridge National Laboratory to compress a 6-millimeter wide amount of benzene, a gigantic amount compared with previous experiments. They discovered that slowly releasing the pressure after sufficient compression at normal room temperature gave the carbon atoms the time they needed to react with each other and to link up in a highly ordered chain of single-file carbon tetrahedrons, forming these diamond-core nanothreads. The team is the first to coax molecules containing so-called aromatic carbon bonds to form larger-scale molecular structures in the shape of long, thin nanothreads. The thread's width is phenomenally small, only a few atoms across, hundreds of thousands of times smaller than an optical fiber, and more than 20,000 times smaller than average human hair. The scientists confirmed the structure of their diamond nanothreads using a number of advanced techniques. Parts of these first diamond nanothreads appear to be somewhat less than perfect, so improving their structure is a continuing goal of the program, as is figuring out how to make the nanothreads under more practical and larger-scale conditions. Other co-authors include En-Sher Shu, Vincent Crespi, and Nassim Alim of Penn State, and Stephen Davidowski of Arizona State. These diamond nanothreads promise extraordinary properties, including strength and stiffness greater than that of today's strongest nanotubes and polymers. The threads have a structure that's never been seen before. This image is credited to the Vincent Crespi Lab, Penn State University. With the independence for nimble pursuit, Carnegie scientists tackle some of the most profound challenges in modern science, fundamentally changing what's possible for us, our planet, and our universe.